In this video, I'll talk about network address translation, how it works and why we need it. But first, let's hear a bit of backstory. Where do these little baby IP addresses come from anyways? Back in the late 70s, a couple of clever researchers were thinking about how long IP addresses should be. Why is this important? You have to consider that in every data packet we have to encode the sender IP and the receiver IP. If we only reserve a few bits to encode an IP address, we can keep packet sizes small. However, we'll also have few IP addresses to hand out to people. If on the other hand we choose to have lots of bits to encode an IP address, we'll have lots of IP addresses to hand out, but we'll also have huge packets, which increases the communication overhead. So as you can see, there's a bit of a trade-off going on here. You can either have small packets or lots of IP addresses. They ended up deciding that they'd go with 32 bits for an IP address. That left them with roughly 4.2 billion IP addresses. You have to consider that back then, the internet, which wasn't even called the internet back then, was just a toy for academics. It was definitely not meant for regular people like you and me. And that's what's known today as IP version 4. Now hang on a second, let's do a bit of math here. We have 4.2 billion IP addresses to hand out, but we also have 7 billion people living on this planet as of 2012. And also consider that each of those 7 billion people may want to use multiple devices to access the internet. So yeah, we have a bit of a problem on our hands. What are we going to do about this now? Because clearly having only 4.2 billion machines on the internet is not gonna be an option. We have to figure something out. And there is a fix, but it's, as you'll see, a bit of a workaround. Let's keep it at that. There is in fact a way that we can keep using IP version 4 and get more machines onto the internet. Here's a typical home network setup. This is John's laptop, this is Jane's laptop, and this is Jane's smartphone. They're all connected to the home router. That home router, in its turn, is connected to the internet. And when you register with your ISP, you get to use an IP address that is accessible throughout the internet, and that's assigned to your home router. So in this case, we have 12.13.14.15 assigned to the home router. This is a public IP address that theoretically anyone on the internet can send packets to. Our laptops and smartphone also get their own IP address, but instead of getting one of those 4.2 billion public IP addresses, they get a private IP address. That private IP address is assigned to them by the home router and is not accessible from the internet. Now, if these IP addresses look familiar to you, that's probably because they are. This is one of two ranges that are reserved for private networks. All addresses starting with 192.168 are reserved for private networks, as well as all addresses that start with the number 10. You can use these IP addresses without having to worry that some random web server already uses that IP address. They can, because it's specifically reserved for private networks. Now let's consider the connection from Jane's laptop for a second. Jane's laptop has an IP address of 192.168.1.3. Here's an example scenario where Jane's laptop wants to know what the current weather is in Texas, and to get this information, it will try to contact the server at 40.30.20.10 to get that information. To reach this web server, Jane's laptop will have to go through the home router, through the internet, and finally then arriving at the web server. First, Jane's laptop has to send out a packet requesting the information. It says, "What's the current temperature in San Antonio, Texas?" Now, the message here isn't really important. The web server should know what to do with that, and we won't get into that right now, but what you should know is that there is a source IP address here with a source port, and a destination IP address with a destination port. In this case, it's port 80, which is frequently used for HTTP traffic. Now let's send this package on its way, shall we? When it arrives at the web server will process the incoming request and try to formulate a reply. The reply packet will be addressed to the sender, but in this case, because it was sent from 192.168.1.3, it will not be reachable because it's a private IP address. So what do we do now? Let's rewind that tape for just a second. Jane's laptop sends out a packet requesting the current temperature in San Antonio, Texas. It gets sent along to the home router, but instead of sending it right over the internet, the home router does something that's a little bit sneaky. When that packet re-emerges, you'll notice that the source IP address has been changed. This is not the only thing that the home router does. In addition, it also creates an entry in the NAT forwarding table. Now, we'll talk about the NAT forwarding table again in just a second, but for now, all you have to remember is that this thing allows us to know which packets are to be sent to Jane's laptop when they come in, and which packets are to be sent to that smartphone or John's laptop. Moving right along, the packet travels over the internet and arrives at the web server. The web server will now create a reply packet and will notice that the destination IP address is no longer private. No, instead, it's sent to the public IP address of our home router on that specific port. Now that our home router has received the response, it's time for another tiny lie. It creates a packet that looks as if it was addressed from the web server directly to Jane's laptop, which is not what happened, but that's all Jane's laptop needs to know because it doesn't care about how it got there. It just wants to get the packet and get this over with. But how does it know where to send that packet it just received? The answer is in the NAT forwarding table. We just received that packet on port 24604, and that means, if we look in our NAT forwarding table, that we have to change the IP address on the private side to 192.168.1.3 on that specific port over there in the forwarding table. Jane's laptop receives the packet and the rest is history. Jane's laptop doesn't have to care about any of that NAT stuff. The home router completely handles it for Jane's laptop, and it is completely transparent, so Jane's laptop doesn't have to worry about public and private IP addresses. No, this is something the router fixes, and Jane's laptop doesn't have to worry about it. Of course, ideally, every computer would have its own public IP address, which is why we're slowly, actually just slowly, moving over to IP version 6. Remember how IP version 4 had 4.2 billion IP addresses at its disposal? Well, IP version 6 has a lot more, and I do mean a lot, seriously. Try noting 34 and then followed by 37 zeros, and that's how much IPv6 addresses we have approximately. That is a lot. If we can give every computer its own public IP address, we won't be needing network address translation anymore. This means that routers can once again focus on their core business, which is routing packets, not doing awkward switcheroo tricks. Now, I can hear you saying, this is nice and all, but why haven't we switched yet? This IP version 4 thing is a mess. We only have 4.2 billion IP addresses, and NAT is clumsy as hell. Well, it's not that simple. We have a lot of internet infrastructure that was built up over the years, and they all work with IP version 4. So we have laptops, desktops, home routers, but also stuff on the ISP side and web servers, and they all work with IP version 4. All these devices need to have hardware and software that supports IP version 6 before we can entirely switch over, and that is a huge task. Just to give you an idea, the IP version 6 standard was finalized in December of 1998, and yet here we are 14 years later and we're still running on IP version 4. You can see how this is one hell of a task. Alrighty, if there's anything you'd like to see explained, please do let me know in the comments below. Thanks for watching.